So, a balloon. A balloon, for the purpose of calculus, is always going to be considered a sphere. So, a balloon deflates at 4 cubic feet per minute. Find the rate at which the radius is changing at the instant when the diameter is 36 inches. So what makes this problem tricky is that we have many things happening in this problem. First off, we have to take into account that the balloon is deflating. So if a balloon is deflating, then what that means is that that rate of change is negative. The second thing we need to take into account is that we're looking for the rate of change of the radius, but we're given diameter. And we're given diameter in inches, but volume in cubic feet. So we have to take into account units, conversions, and really ultimately, what are we looking for? So assuming the ball or balloon is a sphere, volume of a sphere is 4/3 pi r cubed. We are given dv dt, and it's -4. We're given dv dt as -4. We are looking for dr dt. That's my unknown. And we're given diameter is 36. That means the radius is half of that, which is 18. But again, that 18 is in inches. And my dv dt is in feet. So I want to take 18 inches and say that that is 1.5 feet. So now we're going to take the equation we know and find its derivative. So we're going to find the related rate of volume and radius with respect to time. So dv dt equals 4/3 pi times 3r squared dr dt. Cleaning that up, you get dv dt equals 4 pi r squared dr dt. We know we're looking for dr dt, so we're going to plug in everything we know. So we know dv dt is -4, and then we have 4 pi. We know r is 1.5. So 15 squared is 225. So 1.5 squared is 2.25. 2.25 times 4. Well, and actually I don't even have to do that because this is -4. So I can technically divide both sides by 4. So that becomes -1. So then I end up with dr dt equals -1 over 2.25 pi, and that's in feet per minute. And you can type it in on your calculator, and it ends up becoming -1.41. I feel like the ladder problem is iconic, yet you'll never see it on the AP exam, but it's like the one you start with when we talk about Pythagorean theorem and we talk about related rates. So a 10-foot ladder is resting against a vertical wall of a building. So here's the wall of my building. Here is my 10-foot long ladder. If the bottom of the ladder is sliding away from the wall, so again, the ladder is on the ground, the ladder is moving away from the wall, so it's going this way, the top of the ladder is going that way. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So, oh my goodness, lots and lots of information. So what I do is typically treat my ladder problems or my triangles as X, Y, and Z. So I do the X on the X-axis because that's where we typically put X. I put Y on the Y-axis because that's typically where we put Y, so on and so forth. For me, it's just easier placing X, Y, and Z in their normal coordinate plane system. And what you'll see is that in math, as you go into higher math, they actually call like that Z line the Z plane. And so it's not like just us saying, oh, X, Y, Z. It's actually like mathematically correct in a real bigger sense. So then that's my drawing. So that's my part 1. My part 2 is to write down everything I know and everything I don't know. So again, we're talking about related rates. We're talking about changing. So I have 3 variables, which means I have 3 potential rates of change. So then I go back and I say, okay, what is what? A 10-foot ladder. So the ladder is 10 feet. So the ladder is the length Z. So Z is 10. It rests against a vertical wall if the bottom of the ladder slides away from the wall. So if the ladder is moving away from the wall, is the length for X getting larger or smaller? So is that a positive rate of change or a negative rate of change? So if this is sliding away from the wall, is this length here going to be getting bigger or smaller? Bigger. So that means that dx dt is positive. How fast is the top of the ladder sliding down the wall? So I'm looking for dy dt. I'm looking for dy dt. And dy dt, when I get my final answer, better be negative. Because that length is shrinking. So if you're going to a point, then that's shrinking, it's getting smaller. If you're moving away from a point, it's growing, it's getting larger. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So what length is that, X or Y? X. So what don't I know that I need to know to do this problem? I need Y. So, anybody know what Y is? Yeah. Yeah, because it's a 6, 8, 10 Pythagorean triple. I'm also going to need dz dt. So, dz dt is the rate of change of the ladder. So, think about anything sliding down a wall, right? So imagine my writing utensil is the ladder. Is the length of the ladder going to change as it slides down the wall? No. So dz dt is 0. The ladder's not changing. So therefore it's it goes away. Okay? So then this is a ladder. We're talking about rates of change of lengths of sides. So my equation is Pythagorean theorem. So then I take my derivative. So that's my given formula. Then I need to derive it. Now, what's really nice about Pythagorean theorem, and you can just automatically, if you want to, remember this, since all of them are squared, they all have a multiple of 2. If I were to solve, quote unquote, for like z or dz dt, I could divide this by 2, which is like dividing both of those by 2. So every time you take a derivative of the Pythagorean theorem, that 2 cancels. You actually can just kind of memorize, it goes away. Because it's always going to be a multiple of all of them. And again, that only works though, like, it doesn't work if you're using it for like the diagonal, if you have it solved for a variable. It only works if you have it in the formal Pythagorean theorem. Now let's plug in what we know. We know x is 6, the x dt is 1, y is 8. We're looking for dy dt, so we're going to leave that in our problem. Z is 10, but dz dt is 0, so that zeroes out. And then I'm just going to solve for dy dt. So I get 8y equals negative 6. Divide both sides by 8. And I get dy dt equals negative 6/8, or negative 3/4 feet per second. A 15-foot ladder rests along the wall of a building. If the bottom of the ladder is pushed along the ground towards the building. So now this is the opposite effect. Last time the ladder was falling down. This time we're lifting the ladder to a vertical position. So if you're pushing the ladder to the wall, then the rate of change of the ladder on the ground is shrinking. Okay, the ladder is 9 feet above the ground. So y is 9, z is 15. What is my x? No. If you add everything by 3, it becomes a 3/4 back. 3 times 3 is 9. 3 times 5 is 15. 3 times 4 is 12. I like breakfast. Plug it all in. Solve for y. Now this time, I would expect dy dt to be what? Positive. a second. Alright. So then, taking into account that same problem, same answers, all the same values, what happens to the angles? So again, things can't stay this easy. We've got to talk about things that are not so easy. So we are going to look at how fast is the angle being made with the ladder and the ground. Change. So all the same information, right? You know X, you know Y, you know Z, you know dx dt is -3, and we know dz dt is 0. Assume you don't know dy dt. I know we solved for dy dt in part A, but assume you don't know it. Always assume you only have the given conditions here, because if you found dy dt wrong, now you're using the wrong number in the problem. And they do on the AP exam take into account, they call it like copy error. So like if you get the wrong thing here and they bring it there, and I try to do that even sometimes like on your test. Like if you take something and you have to use it again and what you got the first time was wrong, but you have like the process right. But my suggestion is always, if you don't need to use it, don't use it. So right now we have x, y, and z, and we have dx dt and dz dt. So if we want to talk about the angle, we got to go back to our good old days of SOHCAHTOA. So we're going to talk about SOHCAHTOA. So sine is opposite, which in this case is y and z. So sine is going to use y and z. Cosine is going to use x and z. And tangent is going to use y and x. So if I don't know anything about dy dt, then I don't want to pick a trig function that has y in it. So that's what it ultimately is coming down to. If I don't know dy dt, then I don't want to pick a trig function that uses y. So how do I know which one to choose? That's how I pick the one I'm going to pick. So we're going to say that the cosine of the angle is equal to the length x over z. That's my formula. What do we do with our formula? Well, we want the related rates. So we're going to derive it with respect to dt. So derivative of cosine is negative sine theta d theta dt. Negative sine theta d theta dt. And then on the other side, I have x divided by z. That is a quotient rule. So you got to do ODI minus hi-de-ho all over HOBO. What I do at this point is, and some of the teachers I've heard try to teach, like, and make you use trig and like the triangle length. Instead, what I say is, okay, this is sine theta. Well, sine theta is the equivalent of y divided z, right? So what I do is, instead of trying to figure out what the theta and all of that junk is, I just to replace sine theta with y over z. So this becomes negative y over z d theta dt equals z dx dt minus x dz dt all over z squared. Now, plug in what you know and simplify what you can. So what's really easy and nice is dz dt is 0, so that x dz dt is gone. Now you have z over z squared. Well, what do I know about z divided by z squared? One of them goes away. And just so you can see it, now at this point I have negative yz d theta dt equals dx dt over z. So I'm going to multiply by the reciprocal over here to get d theta alone. That's what I'm ultimately solving for. And what's nice again is my z's end up canceling. So this would be a non-calculator question because you don't need it. You get d theta dt equals dx dt, which is negative 3 over negative y, where we get 1/3. Here's the trickiest part. We're talking about theta. Theta is a radian. So it's 1/3 radians per second. One last one for today. Sand is poured on a beach, creating a cone. So you have sand creating a cone. So imagine just like dumping sand into a pile, kind of forms that conical shape, whose radius is always equal to twice its height. So if the radius is 4, the height is 2. The radius is twice the height. So if the radius is 4, then the height is 2. If the radius was 2, the height is 1. So radius equals 2h. Or h equals half the radius. Either way is fine. If sand is poured at a rate, so anytime it's in cubes, that means it's dV dt. At a rate of 20 inches cubed per second, how fast is the height changing? So the height changing means we are looking for dHdt. How fast is the height changing at the time when the height is 2 inches and when the height is 6 inches? Volume of a cone is 1/3 the volume of a cylinder. So it's 1/3 pi r squared h. Now, we took the derivative of a cylinder, and what happened when we took the derivative of a cylinder? We end up with dr dt and dh dt, right? What's the problem with having dr dt in my derivative today? I don't know it. And I can't find it. Just can't make it up. So this kind of goes back to optimization. So in optimization, when I had two variables and I didn't know one of them and I couldn't use one of them, we substituted or replaced. So in the case of this problem, I have a relationship between radius and height. I'm looking for change in height. So I want to get rid of r. I want to get rid of r. So we're going to replace r here with 2h. We're going to replace r with 2h. So you get 4 pi h cubed all over 3. Now, I have an equation that only has b, and I know dv dt, and h, and dh, which will give me dh dt. So now I'm going to find my derivative. So I get dv dt equals 4 pi h squared dh dt. And then I want to know the difference in dh dt when h is 2 and when h is 6. So dh dt equals dv dt divided by 4 pi h squared. And then if we're at A, you're just going to plug in 20 over 4 pi times 2 squared. And if we're at B, you're going to do dh dt equals 20 over 4 pi and 6 squared. So 20 divided by 4 is 5. So then you get 5 over 4 pi inches per second. And then I get 5 over 36 pi inches per second. So you can see that as the height as it's getting taller, it's changing more slowly. As the cone gets taller, the height is changing more slowly. It's getting wider before it's getting taller. And that should make sense.